All right, let's dive right into this explainer. Welcome to what I like to call a masterclass on solutions. I'm going to be your expert tutor today, guiding you through the exact concepts and, the real calculation logic you need to completely ace your JEE and NEET chemistry exams. We've taken the source material and broken it down so you can truly master the mathematics of homogeneous mixtures.
But hey, before we even look at a single formula, we got to understand why this matters. Understanding solution concentrations isn't just about passing tests, right? It's the literal difference between life-saving intravenous fluids in a hospital and toxic drinking water in our environment. I mean, just a tiny shift in parts per million can completely change how a chemical impacts the human body. It's absolutely crucial stuff.
So, here is our game plan for today. 1. Real-world solution types. 2. Mastering concentration units. 3. The temperature trap. 4. Vapor pressure and Raoult's law. 5. Abnormal molar masses. And finally, 6. A step-by-step exam review.
Okay, kicking things off with Section 1, Real-World Solution Types. Competitive exams absolutely love to test your ability to classify things. And a huge trap is thinking solutions are just liquids. They're not. Take brass, for example. It's actually a solid-in-solid solution made of copper and zinc, which, by the way, is heavily tested in JE. Meanwhile, NEET focuses a lot more on liquid and liquid, biological applications, or even everyday solutions like antifreeze, which is just ethylene glycol dissolved in water.
Moving right along to Section 2, Mastering Concentration Units.
So, for all you future doctors, pharmacists, and engineers out there, units like mass by volume percentage, that's going to be your daily language. It's heavily used in everything from formulating medicines to massive industrial chemical applications. A great example straight from the source is commercial bleach, which contains a highly specific 3.62 mass percentage of sodium hypochlorite in water. Basically, ask yourself, if you have a 100 milliliter sample, exactly how many grams of bleach are you holding? Yep, it's exactly 3.62 grams.
Now, what about when we're dealing with really minute but incredibly powerful quantities, like measuring atmospheric pollutants or ensuring water safety? We use parts per million, or ppm. Think back to that opening quote. Even a microscopic shift from 1 to 1.5 ppm of fluoride completely changes its effect on your teeth. It's also how we measure dissolved oxygen in seawater, where just 5.8 grams of oxygen sit in a million grams of seawater. So if a test asks for the ppm of 5.8 grams of oxygen in 10 to the 6 grams of water, you instantly know, boom, it's just 5.8 ppm.
Next up is the mole fraction, usually denoted by a little x. Guys, mole fractions are the absolute backbone for advanced concepts in physical chemistry. You literally cannot understand vapor pressure or Raoult's law without first mastering how to calculate the ratio of your specific component's moles compared to the whole mixture. It's like finding your piece of a giant puzzle.
Let's do a super quick micro-assessment just to lock this in. If you know the total moles of ethylene glycol in water, calculating the mole fraction of water simply means dividing its moles, that's 4.444, by the sum of both. Well, when you add 0.322 and 4.444, you get a total of 4.766 moles. Divide the water by that total, and you get a mole fraction of 0.932 for water. Easy, right?
Okay, pay close attention here, because this is exactly where most students get completely tripped up on exam day. You have to distinctly memorize the difference between these two. Molarity, with an R, relies on the volume of the entire solution in liters. Molality, with an L, relies strictly on the mass of just the solvent in kilograms.
Let's practice molarity first. Walk through the logic with me. 5 grams of sodium hydroxide divided by its molar mass of 40 gives us exactly 0.125 moles. Since molarity is moles over volume of the solution in liters, well, dividing that 0.125 moles by 0.450 liters gives you a perfectly calculated molarity of 0.278 m.
Now contrast that with molality. It's a slightly different beast. Let's take 2.5 grams of ethanoic acid. Dividing by its molar mass of 60 gives us 0.0417 moles. Now, instead of looking at the total solution volume, we divide strictly by the 0.075 kilograms of the benzene solvent. That yields 0.556 molol. Do you see the difference in that denominator? It's absolutely vital.
Which brings us to Section 3, the temperature trap.
You absolutely have to categorize your concentration units into two families, mass-based versus volume-based. Why? Because you need to be able to predict how they're going to behave under physical stress in the laboratory setting. Notice how molarity is sitting all by itself in the volume-based category.
And here's the temperature trap in all its glory.
If you heat up a solution, the physical liquid volume expands. Because molarity depends on volume, heating the solution completely alters the molarity. However, mass doesn't change just because something gets hotter. Therefore, mass-based units, like molality, mole fraction, and mass percentage, remain completely untouched and perfectly stable, regardless of how hot or cold the solution gets.
Section 4. Vapor pressure and colligative properties. Think about Raoult's law. It states that the vapor pressure of a solution is directly proportional to the mole fraction of the solvent. As the mole fraction of component 1 increases, its partial vapor pressure increases in a perfectly straight linear line. This shows exactly why mastering mole fractions earlier was so essential for us.
Now, osmotic pressure is another massive colligative property. It's actually proportional to the molarity of the solution. This is the exact principle dictating how water flows into or out of your blood cells. If an IV fluid is isotonic, it perfectly matches the 0.9% sodium chloride in your blood, and your cells are safe. But if it's hypertonic, water flows out and the cells shrink. Hypotonic, water rushes in and the cells swell up.
Let's look at Section 5, Abnormal Molar Masses.
Okay, this right here is the curveball examiners absolutely love to throw at you. What happens if a solute like potassium chloride is put in water? Well, it splits into 2 separate ions. That means the actual number of particles doubles, which effectively halves the experimentally determined molar mass. Conversely, ethanoic acid in benzene actually clumps together or associates due to hydrogen bonding, which reduces the overall particle count. Whenever this happens, you must use the Van't-Hoff factor, represented by the letter I, to correct your calculated molar mass.
Finally, Section 6, Step-by-Step Exam Review. When you're staring down a brutal calculation logic problem on your JEE or NEET exams, I want you to follow 3 simple steps. First, clearly identify the unit. Are we using molarity or molality? Second, actively check if the question mentions a temperature shift. If it does, your volume-based units are invalidated. And finally, ask yourself the golden question. Does the solute break apart or clump together? Actually, scratch that. Just ask, do I need the Van Hoff factor?
Let's wrap this whole thing up. From the IV fluids matching your blood plasma perfectly to the solid brass in industrial machinery, mastering the mathematics of these homogeneous mixtures is the absolute key to unlocking physical chemistry.
I'll leave you with this final thought to ponder before test day. Chemistry isn't just a bunch of numbers on a page. If we fail to account for abnormal molar masses and the Van't Hoff factor in a real medical setting, what actually happens to a patient's blood cells when that mathematical error enters the human body? Keep asking questions, keep studying smart, and I'll catch you in the next explainer.